This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Essentially, if we look at this N-type or NMOS type transistor, what we've got is a PN junction between, here at the interface between the N well and the P substrate. And if at any time the substrate or the source, the substrate is at a higher voltage than the source or the drain, essentially what happens is that diode becomes forward biased, and as a consequence, large currents can actually flow and they can actually destroy your transistor. Okay, so essentially that was just a little bit of background of the, some interesting background on the NMOS transistor, and I'll leave it for you to do some further reading to look at PMOS transistors, because what we said is in CMOS we've got both N-type and P-type transistors, right? And essentially, what distinguishes between an NMOS and a PMOS transistor? Okay, I'll give you a hint, the carriers. So what's the difference in the carriers? Perfect. And what does it also say about the threshold? What do we know about the threshold voltage for an NMOS and a PMOS device? And specifically what we're talking about here is either enhancement or depletion type devices. But what did we say?
NMOS need to above the threshold.
Yes.
PMOS need to below.
Perfect. Perfect. All right. Excellent. Now, I spent a little bit of time talking about the threshold voltage and the like, and deriving some equations. In hindsight, probably not appropriate for this course. The more I think about it, this I'll leave to my colleagues teaching you about device modeling. But the only reason why I wanted to talk a little bit about this was essentially that there is this concept called body effect, right? And we talked very briefly about body effect. Can anyone remind me what is body effect? Perfect. Yeah. Essentially, what we're saying is that the threshold voltage depends on the source to substrate voltage, right? And just in order to avoid writing VSS, I've written it as base. So what we're saying is the source to base voltage is essentially affects, if it's non-zero, it actually affects the threshold voltage. And essentially what happens as the VSB increases, the threshold voltage increases. Why is that significant? The reason why it's significant is we do use this type of structure in a couple of places, and we'll talk a little bit about, hopefully we'll get to it in this lecture, where we start talking about tri-state buffers and the like, and essentially what we'll show is in certain gates, what we do is we actually stack multiple transistors in order to be able to build that specific structure. Now, as your colleague has correctly pointed out, the reason why I'm emphasizing this, or wanted to point out, to make you aware of this, was essentially that as you stack more and more transistors, you affect the threshold voltage, so you've got to be a little bit careful. Now, adding 2 or 3 transistors is usually fine. If you start adding more, it starts becoming more problematic. And it becomes problematic only in bulk devices. And as I mentioned last lecture, some of the new, more advanced processes are no longer produced on a bulk process. They're actually built on a silicon isolator type process. Now, what I suggest that you do is, before you go to bed at night, maybe look up silicon and isolator, and you can find out some more details. And if it doesn't put, if that doesn't put you to sleep, I don't know what will. But anyway, it's something exciting, interesting, or potentially exciting, or maybe very boring for you to look at. Okay, now the other thing that the other reason why I briefly talked about the body effect was I also said that we might want to use these stacked transistor configurations in power amplifiers or actual drivers, right? And specifically more, where we potentially are more interested in it is if we're using, if we're trying to get high power out of, how do you call it, power amplifiers on a CMOS process. And essentially what you've got when you're trying to get the power out of a power amplifier, or trying to get more power out of a power amplifier, I should say, essentially the power that you get out of it goes as V squared on R, right? R is the output impedance, V squared is the voltage that you can actually swing. Right, now if you are on a, say for example, a 130 nanometer process, usually the maximum voltage that you can swing or that is available to you is about 1.3 volts, right? That's the maximum that you can put across one transistor. Now as you go to 65 nanometer or even 28, things get a little bit more complicated, but usually you've got about 1 volt. So if you think about it, if you're trying to build a power amplifier and you weren't stacking transistors, what's the maximum power that you could get out? Absolute maximum power. If you were feeding a 50 ohm load. Sorry? I said it's a, say it's a 65 nanometer process, so 1 volt. What's the absolute maximum power that you can get out?
50.
Sorry? Yeah. Right, exactly. Okay. So then you can actually work out what your maximum power is. Now, if you can work that out in dBm, it's probably, and it will be a little bit less than that because you've also got a threshold voltage and whatever, right? It's probably going to be half volt squared over 50 ohms. That's the maximum you can get out. So therefore, you don't get a lot of dBms out, right? A lot of watts, right? And if you want to get one of these that transmits at far distances, well, you've got to start doing some interesting stuff. And under those circumstances, you would start stacking transistors. So therefore, you can maybe put a 1 volt. You can go for a 2 volt supply or a 3 volt supply, or you can start doing some other tricks in order to get higher power output. All right. So so let's now talk about these MOS design equations. And then essentially what I'm doing here is, so we're starting with some new material, and hopefully you've all seen this before, but essentially, as you can imagine, or hopefully you know, there are 3 regions of operation for a MOS transistor. Okay? There is the cutoff region, or subthreshold. What does that mean? Yeah, it's cut off, yeah. So the threshold voltage, so the input voltage is below threshold, and it's cut off, meaning that doesn't be current. Yeah, perfect. Linear region. Okay.
Currents will change linear with the input voltage.
Right. So essentially, what we've got there is okay. So there's a relationship between. Okay. So essentially, what we're saying is that the drain current depends on VDS, the drain to source, right? Essentially, when you're in the other region, which I'm going to talk about, which is saturation, essentially what happens is that your current that you're getting out is essentially independent. After a certain voltage, it's independent of your drain source voltage. Right. So therefore, essentially, what happens is, and we'll show some graphs. If you've probably seen these graphs where you draw drain to source current versus VDS. Above a certain region of VDS, right? What happens is, irrespective of what VDS is, right? So provided it exceeds, so VDS is greater than VGS minus VT, the output current is independent of VDS. Right? That's essentially that you're in saturation. In this region where you've got this dependency on VDS, we actually describe it as the linear region. It's not actually linear. You do have a semi-quadratic term, but depending on how close you get to, depending on how small VDS is, you can actually see that it's a linear. It's almost linear. Now, if you're building an amplifier, right? Where would you build this amplifier?
Saturation.
Okay, good. I like it. Yes. Why?
Because the current is not depends on the supply voltage.
Okay, good. Yes. So where did you learn that? That's good.
From another subject.
Sorry?
From another subject.
Electronics circuit design.
Fantastic. Good. I like it. Okay. And so you did MOSFETs in there.
But more like focus on small systems.
Yeah.
All right. Okay. All right. Good. 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 Fantastic. And who's teaching that? James. Okay. Fantastic. All right. Good. Good. I like it. All right. And then what we've got is, of course, the saturation. And what we've said there in saturation, we've got the voltage. Sorry, the current doesn't depend on VDS. Now, if you're designing this power amplifier, essentially what you're doing, or any kind of amplifier, you know, and you're in saturation, you're actually, as you're changing VGS, you're moving up or down these. I don't know what's happening. Okay. All right. Let me see if that helps a little bit. Okay. So essentially, what you're doing is you're moving along these lines, right? So you draw your load line, and then you're moving across those lines. Perfect. So now let's look at a very simple circuit, and it's supposed to illustrate, how do you call it, the function and some of the challenges and the operation in some of these regions of this transistor. So what I'm going to talk about is the CMOS inverter. Okay, can someone tell me what an inverter is? What? You got a logic 0, if you put a logic 0, you get a logic 1, if you got a logic 1, you get a logic 0 out of it. Now, you've probably seen it, you know, the structure of a PMOS inverter. Who hasn't seen the structure of a CMOS inverter before? All right, you've all seen it. Good. All right, so essentially what you've got is you've got a P-type transistor and an N-type transistor, right? And they're stacked one on top of each other. You've got an input, which is the input to the two gates, and essentially what you do is, you know, the midpoint between these two transistors is your output. Okay, can someone tell me how this circuit actually works? It's the simplest circuit, right? The simplest logic gate. And anyone want? I mean, you've even got it in the notes, right? Today's lecture notes, I didn't put them up there deliberately so I can actually play this game a bit better. But can someone tell me how this inverter works? Okay, so let's look at all the regions, right? So let's look at the region where the input, and essentially the input is the input to the gates, is less than the threshold to the N transistor, to the NMOS. Okay? So what we know is the N device is in cutoff, the P device is in its linear region, but there's no current that flows. Why doesn't any current flow? Which one's cut off? N-type. Perfect. Okay. And the output voltage is? Ooh. Almost right. Almost right. What's the output? What's the power voltage? Right. Now you can think of it in the most simplest of terms. What you've got is, for argument's sake, and this is very simplistic. This transistor is open. You can think of it, if there was a switch, that one's open, that one's closed, right? So therefore what you see at the output is VDD. Okay? Excellent. Now let's look at the region when the in is greater than the threshold, but it's less than half the supply rail. So what we see is, under those circumstances, We can see the P device is again in the non-saturated or linear region. The N device is in saturation, and essentially the P device, it being in the linear region, is actually acting as a resistor. And what you can also show is the N device is acting as a current source. Right, and if you're drawing, essentially if you're drawing the voltage, what you're seeing here is we're in region B, which is essentially what we're seeing is the voltage is beginning to decrease, the current is beginning to increase, but it's somewhere in near the region of half the supply. Right. Okay. Now, what we want to now look at is what happens at exactly this point C. Now, in this particular case, when you're in region C, essentially what you see is both the N and P type devices are in saturation, and that's the point where you get maximum current through that device. Now, we then proceed to region D, which is this region here, which is essentially the input supply is between half the supply and the supply. And under those circumstances, we know that the P device is in saturation, while the N device is now in the linear region. Right? And then particularly what's important to note here is that from the point C to D, we're actually seeing a decrease in the current through the device. Okay. And in the last region, what we're able to see is that this is defined with the condition that the supply is close to VDD, in which the P device is cut off and the N device is in the linear region. What do we suspect the voltage to be there? 0. Perfect. All right. So what we're showing here is the simplest operation of a circuit, one of the simplest gates that we've got in CMOS, right? And essentially what I've done here is drawn a little table for you where for each of the regions we've got the input conditions, what's happening to the P device, what's happening to the N device, and the output. And I've written the output in terms of these equations. I guess other than, for interest, I wouldn't spend too much time on them. The only thing that's important, however, to note is that the output voltage, and this is something that you need to be a little bit aware of when you're designing these gates, is that there's a ratio of the current between the P and the N type elements, right? The P and the N type transistors. And essentially what you want is, in order to get what you strive is to get this ratio being close to 1, right? It's not necessarily close to, under normal circumstances, if you had the same transistor with the same geometry, would you expect it to be 1? And if no, why not? I'll give you a little bit of a hint. If I write beta here, right, and beta is epsilon, thickness of the oxide, width to length, ratio of width to length. So let's assume I said that they're exactly the same size. So for width and length and Tox and E being the permittivity are all the same, why wouldn't the betas be the same? Mu is different, right? Okay. So would you expect mu for the NMOS to be higher or lower? Higher, yes. Why? I got that. I got myself into a bit of a muddle last time. I was going to say, oh, because they weigh less, right? Because mobility is, but it's not actually that, right? So the mobility of holes is a lot less, probably a half to that of electrons, right? So therefore, what it means is, if you want to be able to have a good inverter, a good and balanced inverter, what you should actually do is you will need to have the size of your P transistor to be almost twice as large as your N type. Right? Otherwise, the current and the voltage that you actually receive at the output is dominated by your P-type device otherwise. Right? Now, what's the disadvantage of doing that? Right, so therefore you've got balanced current, but bigger devices also mean, but you want this, the NMOS has got a large current also, you're trying to balance the current. But it's the same current and the same voltage across it. Capacitance. And why is capacitance important?
Because it's limit the speed of operation.
Perfect. Exactly right. Right, so therefore, and that's part of the thing that we're going to learn as a later part of the course, which is, hey, you know, you got this trade-off. You want essentially, there's multiple things that limit your performance, but one of them, of course, is your drive capability. So therefore, if you've got a transmission line, you want to charge it up in order to propagate the signal as fast as possible. You want as much drive, but then you actually start, in order to have sufficient drive, you need to make your transistors larger. So therefore, there comes a time where the capacitance of the transistor begins to dominate, and that's where it starts becoming a little bit problematic. Right? Okay, now who's seen an AND gate? This is new stuff, so therefore I can actually start asking questions. You can't look at the notes. Yes. NAND. You haven't seen it? Or you have seen it? Okay, alright, okay. Oh, no, I haven't drawn... Oh. Okay, I haven't drawn... you see, I've done a big boo-boo here. Oops. Yes, because you see, so in the note... okay, I haven't put the notes up, so it's fine. I'll have to... Otherwise, I'm deliberately short-circuiting gate A. Okay. All right, so can anyone tell me how this works? All right, so what we've got here is a NAND gate, right? So we've got a couple of PMOS transistors and a couple of NMOS transistors, right? And essentially, what I'm, this is VDD, this is ground, and essentially what we've got is, what I've denoted is the various logic states, right? And here, for argument's sake, when I say 0, I mean ground voltage, and when I mean 1, I don't mean 1 volt, I mean actually VDD, right? So how does this work? Can someone just give me a very quick indication? You must have done this all before, right? Okay, so tell me how it works. All right, so what happens when A is high? Or when let's start look at A being 0. A being 0, which means ground. What happens to the P? It's on or off? On. Okay, so they're on. Okay, good. What happens to B? What happens to these NMOS? If B is 0, these NMOS devices off. Perfect. So A off, B off. So therefore voltage is, the output voltage here is what? High. Yeah, perfect. All right. Let's do, for argument's sake, let's do 0, 1. All right. PMOS device, the PMOS device is on or off? On. Okay. This PMOS device is on or off? Off. Okay, good. All right. So therefore, the only thing that's happening is this current is, this is connected. That one's off. Okay. All right. So what happens down here? Okay. B is on. How about this one? No. A is 0. So it's off. So therefore, current can't flow down here. Even though this switch is open, current can't flow because this switch is off, all right? So therefore, what we've got is this point is at the supply rail. There you did. Okay. Who wants to guess 1, 1? give a top of both off, so therefore, and this is pulled down to ground, so therefore that's ground. Okay, perfect. All right. Now, essentially, what I've done is also drawn you a NOR gate. I won't go through it, but you know, it's worthwhile having a look at it at some stage. And I apologise. You know, again, my drawing is terrible. In order to show what the what this NOR gate looks like, and then you just go through the logic, and convince yourself that if you've got these inputs, you get that out. Now, what I'll do is I'll just remind you of this. I mean, essentially, I'm going to go through and talking to you about, well, if I had two NMOS transistors, depending on what G1 and G2 is, if they were in series, if I've got, if the inputs are 0, this series is off. If one of them's on, it's still off. And it doesn't matter which one, both have to be on for this to be on. And likewise, if I've got a PMOS, I'm showing you essentially this type of structure or what happens. Now, here I'm beginning to talk a little bit about when I've got two of these transistors in parallel, what happens. And essentially what we're doing is saying, well, one's off, one's on, and essentially work out, if current flows. Okay. Right, and likewise here when I've got NMOS or PMOS devices, right? Now, has anyone talked about or seen or understand what a transmission gate is? Okay. All right, essentially what we'll do is, all right, so the first thing I want, before I go into what a transmission gate is or a pass transistor, there's this concept of strength and the strength of the signal or strength of the source, and essentially we say that a source or a signal has high strength if it approximates approximately how well it approximates an ideal voltage source. And generally, a stronger signal, the more current you can source or sink. And the thing here that's important is that an NMOS transistor is almost a perfect signal when passing a 0 or low signal. But it's not ideal for passing a high signal, right? Because what you can think of is it's got some internal resistance, and therefore it actually doesn't act like an ideal an ideal voltage source. Why is that significant? Why do I care about that? I've told you potentially some useless information. Maybe. Why is that significant? Then let me ask you a question a little bit differently. Now, I drew for you somewhere an inverter. Right, and in that inverter, I put the PMOS on top and the NMOS on the bottom, right? You could easily put the NMOS on the top and the PMOS on the bottom. But nobody said to me, hey, Stan, why did you choose to do it that way? Right? If you looked at our switching diagrams, like the stick diagrams that I was just showing you before, you could easily transpose it, right? You could put an NMOS, PMOS, or PMOS and NMOS, and that would still act as an inverter, right? Why don't you do that? Or why isn't that done? It must be, I'm a very simple creature, right? You can tell that I'm not very advanced, because the answer must be here, right? Because I'm talking about signal strength, right? Essentially, what happens is a PMOS device actually has high strength when it's pushing a 1, and an NMOS device has a high strength when it's pushing a 0, or has a 0, right? So therefore, in order to have the best gate that you can actually produce, so therefore you're closer to the supply rail or to ground, the way that you would configure it is PMOS, NMOS, right? So don't ever produce a inverter using NMOS and then PMOS, right? It's not what you would do. You agree, Mr. Okay. All right, cool. Now, so the other thing that we want to do is sometimes we want to produce switches, right? And we want to be able to, you know, for example, we've got a signal here and we want to send the output to point B, right? So sometimes, for whatever reason, you know, we want a switch, and that could be a TR switch, you know, for your, this isn't the best way of doing it, but, you know, some kind of switch or whatever. This allows you a mechanism by which you can actually control what the voltage is at this point B, right? And what I'll do a little bit later is also talk about multiplexers and tri-state buffers and the like. But essentially, what we're showing here is in order to build a transmission gate, in order to be able to pass both a low and a high signal, the way that we actually do that is we essentially put in parallel a PMOS and an NMOS device. And essentially what we do is, depending if we want to, when we want to transmit the signal A to B, essentially what we do is we control, you know, the gate signal. So therefore, if the gate is 0 and G bar is 1, this is an open circuit. If it's 1 and 0, it actually acts as a short, and it allows us to transmit both zeros and ones appropriately, or with minimal noise or minimal distortion. Okay, so that's the concept of a transmission gate. It's something, it's critically important, and it's used in multiple places. Now, question, what's a tri-state buffer? And why would we ever use a tri-state buffer? Especially to my colleague there who wants to be an FPGA designer. Why would you ever use a tri-state buffer?
Asynchronous communication.
Asynchronous communication. Maybe. No, I don't know. I mean, it may be useful, but okay. So, but usually, what you've got is you've got an output, right? And your output could be both input or output, or you might want to, for example, connect multiple things to a bus. Who knows what a bus is?
The data bus.
Yes. Yes, the data, not the bus that you got to yes. Right. So you got a data bus, right? You essentially have a collection of lines or one line, and you want to be able to put a signal onto it, right? Now, the question is, you might want to be able to, it's almost a way, you know, a mechanism by which multiple devices can communicate to each other across this mechanism, right, which is this line. Right, so you can think of it as, suppose I wanted, sorry guys, so suppose you had two peripherals, right, and you had something here, right, and you wanted, so they're all connected, right, and you wanted one to talk to this. So suppose you wanted, you know, A to talk to C, right, or so what you would do is you would put B into this high impedance state, right? You don't want B to be driving the bus, because then you actually have contention. You know, the A might be driving and B is driving. What's the voltage, right? If two elements or two components are trying to push at the same time, well, what's happening? So essentially, what tri-state buffers allows us to do is essentially develop a transmission gate type of device, but it has one difference, a couple of major differences to a transmission gate. And that is, and the most important difference is that it also has a high impedance state, right? Now, so let's talk a little bit about this. Have you seen tri-state buffers before? Have you done it in your lectures? Yes. Okay. All right. Okay. In here in this course.
No, is ESD, electronics design.
Oh, you've done it. Okay. All right. Good. Good. All right. So essentially, what's happening there is we design these tri-state buffers, which I'm glad to hear that you guys are doing this. Is essentially that you're trying to connect multiple outputs to a bus or to a common output, and essentially, when the enable signal is high, the output equals to the input. Okay, and my move is this too high now? Yeah. Okay, and when the enable signal is low, the output signal is left floating, right? And float. What do I mean by floating? Sorry, it's you don't care. It's some value. It could be 0, it could be 1. But it's not driving the bus, right? So when you drive it, it actually pushes it high or low, right? Now, I've used tri-state buffers, and one of the things that I'm going to introduce here is the concept of a non-restoring circuit. Who's heard of the concept of non-restoring circuit? Okay. Essentially, a transmission gate, what it does, or a lot of gates, not the inverter, but a lot of other gates, what happens is that if you've got noise in the input, you get noise on the output, right? And essentially what happens is that noise continues to propagate. A restoring circuit is essentially, provided that you've got some logic on the input, yes, some logic at the input, what it does is it cleans up the signal and you get it back to the original signal, right? And that's what the concept of a restoring circuit is. Now, an inverter is a restoring circuit if you do it as the way, PMOS on NMOS. That's a restoring circuit. Some of the other gates like NAND and that are not restoring, right? But essentially, the reason why we want restoring circuits is they remove noise, they get our signal back, but also what we'll show is that in the future, that if you've got non-restoring circuits, they also increase the propagation delay through that system. So essentially what you want to do in many cases is actually occasionally put restoring circuits between the various outputs in order to be able to clean up the signal and also reduce your propagation delay in combinatorial logic. Right? One of the other tricks that you can actually do is actually, use sequential logic or synchronous logic, and that you're gating and then converting, and that helps you, right? Now, in this particular case, I've got a tri-state inverter, and essentially what I've done here is actually show how this tri-state inverter actually works. You can think of it as I've got the input that I want to get to my output, but it's inverted. So essentially, what I'll do is I'll put an inverter here. So therefore, if I want A, I'll get A bar, and then A bar will become A. But essentially, I've got two enable signals. Now, as you can see, these two enable, I've got an enable signal and its complement, I should say, rather than two enable signals. Now, when the enable is low, right, what I see, what you can actually show is that this and this parts, the PMOS here, because it's enabled bar, and, sorry?
It looks like open switch.
Yeah, it's two open switches, yes, exactly. So therefore, this output Y is floating. And likewise, when you've got enabled being equal to 1, what essentially you've got is you've essentially got an inverter, so therefore A equals to A bar. All right. So now tri-state buffers are important, especially for outputs. So that's the reason why I've done that and introduced you to that. And then the other thing that I'll introduce today, and I'll go very quickly over the next few minutes, is multiplexer. Who's seen a multiplexer before? Yes?
Yes.
Okay, how does it work?
Forgot.
Okay. All right, why would you use a multiplexer? Yes. So you want to work out which output, right? So for example, if you want to select A or B, this actually gives you the circuit on how to do that, right? Okay, so that's the reason why you use a multiplexer. Can you tell me an example where there's a multiplexer, like in like a real world example where there's multiplexers? Sorry? DAC. Probably. Any memory, right? When you're trying to address memory, right, you need a multiplexer, right? Calculator. I'm sure it's got one in there, right? But yeah, but what I was thinking, what I was asking is, like, you've got an array of memory, and you want to either read or write at a particular location. You've got a multiplex, right? And essentially here, what I'm talking about is how you can actually build this multiplexer, and essentially it's a couple of pass-through or transmission gates, and it allows you to essentially choose between D0 or D1. In this particular case, it's non-restoring because, again, the transmission gate's a non-restoring circuit. Now, and we've talked about this, I won't go into too much detail again because we've already talked about it, but what you do is, I guess all I'm trying to point out here, this is the simplest circuit which actually implements a multiplexer, but the truth of the matter is that, if you're trying to build a multiplexer in real life and, if you've got multiple of them, you wouldn't actually produce it like this. You would actually use non-restoring gates to actually implement it. And essentially all I'm showing here is, depending on, if I've got, one of the switches selected, essentially what it does is, depending on S bar, if S is 0, I don't really care what X is, the output is Y, the output is D, the output Y is equal to D0, and likewise, if S is equal to 1, essentially I don't care what D0 is, the output is equal to D1. Right, that's what I'm showing there. And here, what I've done is, for everyone's benefit, because I'm sure all of you go home and build circuits, what I've done is actually shown you how to implement a restoring, albeit inverting, multiplexer. And essentially what I've done is I've used a couple of tri-state buffers in order to do that. So it's got a few extra elements, but again, it's restoring rather than a non-restoring configuration, which has noise advantages and also propagation advantages. All right, now we're going to talk a little bit about sequential circuits and latches and flip-flops before we finish. Can anyone tell me what's the difference between a combinatorial and a sequential circuit? I've got the answer there, so you can actually read it, but I mean, it'd be nice if someone said, hey, Okay, so combinatorial essentially means that the output now depends on the input now. That's it. Right? There might be some propagation delay, but output is a function of the current inputs. Whereas a sequential circuit, essentially what I'm saying is the output now can depend on past states. Right? And what we do is, there are some advantages of doing sequential circuits and clock designs. Can anyone tell me why we do that? Why we would potentially use sequential circuits, or some examples of using sequential circuits? Sure. Yeah. Feedback to store values. Like, for example, if you wanted to build a memory, right? We talked about, flip-flops last time. In order to store memory, that's a sequential circuit. What else? Sorry? The circuit, yeah. I mean, essentially, what the other main reason, rather than having state, is, and what we'll see, and the reason why we're introducing this and talking about this, is also that in combinatorial circuits, unless they're very small, it's really hard to control the propagation delay, right? As they become larger, the propagation delay becomes a little bit more difficult to deal with, right? Whereas in sequential circuits, especially if you're clocking and maintaining the output, it means that it becomes a little bit easier for you to do the design and make sure that you don't violate your setup and hold times and the like, right? So does everyone know what a setup and hold violation is and all that kind of stuff? All right, good. We'll learn about it in this course. Because if you said that, yes, you know it, then I'd be like, oh, geez, what am I going to teach you in this course? Or this part of the course. Okay, so the first thing, combinatorial circuits, as I said, you know, it's just combinations of ands or ors and ors, blah, 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 right, in order to do some kind of logic. Now, sequential, we said, is state dependent. And now what we're going to do is in these state-dependent circuits, we're going to start talking about two types. We're going to talk about latches and we're going to talk about flip-flops. Right. What's the difference between a latch and a flip-flop? They're both clocked, so don't say to me they're not clocked, right? So what's the difference? Now, they both got feedback. So who's used a flip-flop? Okay, what did you use it for?
I remember I did a course in TSD.
So what was this?
In what?
TSD.
TSD.
Digital system
Yes,
design.
digital system design.
Yeah, okay.
And then we learn DLANG and flip-flops and R circuit. Yeah, RS circuit.
Sure, and?
I can't remember the details.
Okay.
Storage data.
But both of them could store data. Both of them could store.
Level dependent, one is edge dependent.
Yes. Yes. Now, was that on the, well, okay, so I've written level sensitive. Is that, did you know it from the course or did you actually see it here?
From previous.
Okay, good. All right, good. Okay, that is absolutely right. Okay, so what we've got here is latches essentially maintain their state, but they critically depend on the voltage of the clock, right? So therefore, essentially what happens is you get a transition in states as essentially as you go from zero, not as you go from zero, you get a transition when you go from 0 to 1. Whereas in a flip-flop, what I'll show is you actually, that transition occurs at the edge, right? You almost get a sampling type of effect. Okay, so what I'm doing here is essentially talking about how a D latch actually works. Essentially what it's got is we've got two transmission gates and we've got two inverters, and essentially what happens is you've got your data at this point. When the clock goes high, essentially what happens is this transmission gate is transparent, so therefore whatever the data here moves to this point. When the clock goes to 0, essentially what we do is we establish the feedback, and whether the value of this D is now held at that value, right? So this feedback allows us to actually hold that value Q, right? And you can actually convince yourself that that's the case. But the thing that's important is that these devices are level sensitive, right? As your colleague has correctly pointed out. So it really depends on the level of the clock, right? So therefore you can think of the situation where your clock's beginning to slowly, the voltage of your clock is slowly beginning to droop, and if that's the case, or you're getting an increase, essentially what happens is the state changes, right? Whereas what we're going to talk about next is these flip-flops. And essentially what happens with these flip-flops is they're edge-triggered devices. And essentially you can actually draw these edge-triggered devices, or for example in this particular case we see a D flip-flop, again created with multiple transmission gates. But essentially it's you can think of it as two latches, one after the other, right? The only difference is that the clock signals are now inverted between the two latches, right? And as a consequence, if you actually draw the switch diagram, essentially what happens is, you know, as the clock is transitioning from positive, from 0 to positive, essentially what happens is, at this point of the positive edge, you actually sample the signal, and that's the value that is held at the output. And what it also indicates is that irrespective of what's happening to this supply line, you only sample it at the positive going edge of a clock. This is, in the way that I've configured this one, the way that I've drawn it is it's just a positive edge-based flip-flop. Okay, and that's, I think, it. That's all I had for you today. What I introduced was some of the basic gates, talked a little bit about latches, tri-state buffers, transmission gates, non-regenerative circuits and regenerative circuits. And what we're going to do next lecture is I'm going to start actually talking about how to calculate propagation delay and drive strength from these gates. So in order to be able to calculate how fast can you make these circuits run, and how can you design so that they operate even faster so that they can meet your design requirements. Okay. And you're all, I guess, busily reading away, trying to learn everything for your exam, or not exam, test. Is that correct? All right, cool. Yes.
I want to know for our middle test, is that for this middle test and this
No, I don't even know what's on it. No. The test, no. I've given you I've given you.
Yeah, I see that.
I've told you what 3 questions are.
Yeah.
I can't tell you any more, right? I mean, you've got the questions.
And do you have any problem set or exercise?
I've given you the problems that I've given you.
Just one.
Yeah, but that's got everything in it, right? And then the rest of it, you can actually just look it up. I've given you examples also that you can go through. It's got everything.
You mean I just go through all the examples in the lectures and
The notes, if you look at POSA, also that'll help. If you look at POSA and look at the examples.
Yeah, I just follow that book for just one chapter.
Yeah.
And for the digital part, is there any reference book?
I think, what I'll do is I'll probably follow VLSI Design by Westy. What I'll do is I'll put it up. All right? Okay. You can, and also, Yeah.
Just a very short question.
Okay, yes.
The book name?
I'll put it up. I can't remember it. It's VLSI Design or something. Okay, it's not. I'll put it up. Just remind me. I'm more than happy to tell you what it is.